Hello everybody, today we're going to be looking at 4.2 graphing exponential and logarithmic functions. So we're going to take a look without the graphing calculator and see what the shape of exponential functions looks like. Last class we learned about exponentials and we reviewed some of the exponential laws from grade 10, and today we're going to see what it looks like as a graph. So this connects really nicely with the chart that you made last class. So first let's graph 2 to the power of x. And we'll just do this by putting in some points. So 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And you start to see a pattern. As you go up, you multiply by 2. As you go down, you divide by 2. So 2 to the power of 0 is 1. And when we have negative exponents, we get fractions. Now if you plot these points, you'll see that the graph has an asymptote. So 0, 1. 1, 2. 2, 4. 3 will be 8. 4 is 16. And as we go onto the negative side, the numbers get smaller and smaller and smaller, but they'll never quite equal to 0. So we have a horizontal asymptote for an exponential function. So it starts really slow, and then all of a sudden when it crosses the y-axis, it goes up with a vengeance. Now g of x is even more interesting. G of x is 1/2 to the power of x. So to figure out the points on this graph, we just plug in the values. 1/2 to the power of 0? 1. Everything to the power of 0 is 1. 1/2 to the power of 1 is still itself. 1/2 squared is 1 squared over 2 squared, which is 1/4. And then 1/2 cubed would be 1/8. Now what happens when we go backwards? 1/2 to the power of negative 1 is 2. When you have a negative exponent on the outside of a fraction, you can flip the fraction over and change the exponent to positive. That's the rule from grade 10. Okay, so it's 2 to the power of 1. 1/2 to the power of negative 2 is the same as 2 squared. So this is a very interesting effect. They both have the same y-intercept. And then as you get bigger and bigger and bigger, the numbers get closer and closer and closer to the asymptote of 0. So do you notice which transformation could take you from one graph to the other? Is it the inverse? Not quite. It's a reflection. These two are reflections in the y-axis. And the reason why is because you can write 1/2 as a power of 2. 1/2 is the same as 2 to the power of negative 1. And we did that as a warm-up. So this is the same as 2 to the power of negative x. So you just change the x from positive x to negative x. So it reflects it in the y-axis. Okay, so the general principle is that when you're graphing an exponential function, if b is bigger than 1, so if the base is a large number, then the graph increases as x increases. And it has a horizontal asymptote. And that horizontal asymptote is the line y equals 0, the x-axis. And it doesn't matter what the base is. You can be graphing 1,000,000 to the power of x or pi to the power of x. These graphs will always cross at the same y-intercept. No matter what, the y-intercept is 0, 1. Because it doesn't matter what you choose for the base, 216, if you put 0 in for x, you're always going to get 1. Now, if b is a fraction, and this is just like what we graphed above, like 1/2 to the power of x. If b is a fraction, then the graph decreases as x increases. When you go to the right, it starts off high, and it quickly decreases, and after it crosses the y-axis, it'll get closer and closer to the asymptote. It also has a horizontal asymptote. Of y equals 0, and it also has a y-intercept of 0, 1. So now we're going to use our transformations to be able to draw all sorts of variations on exponential functions. So we can use the graph of 2 to the power of x to draw the graph of 3 times 2 to the power of x minus 1 plus 1. Now, if I wrote this in function notation, this is the same as, let's see, how did I change x? X became x minus 1. So that means that inside of the function, I change it to x minus 1. Okay? And then I added 1 on the outside and multiplied by 3. Okay, so the function, the f part, is the 2 to the power of x. 2 to the power of x is my f of x. Okay, so the 3 gives it an expansion vertically 3 times. And the plus 1 will move it up 1. And the minus 1 inside is changing the x value, so it's going to move it right 1. So now if I draw my 2 to the power of x, just like I did before, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 won't fit, and then backwards I get all these fractions that get closer and closer to 0, but never quite touch 0. So there's my graph of 2 to the power of x. And now I can take the points on that graph and find out where they move if I do the transformations. So I'm just going to start with the point 0, 1. And first, now I'll go left to right. I don't have to worry about factoring b because there's no b value here. So the first thing I'm going to do is expand 3 times vertically. So I take my y value times 3. Then I'll move up 1, or, well, I can go right to left, left to right. So times 3, then move it right 1, and then move it up 1. So my new graph has a point 1, 4. The other point that's really important is the very first point when x equals 1. So first thing I'm going to do is multiply my y value by 3, and then move it right 1, and then move it up 1. So 2, 7 is a point on my new graph. Let me take the point 2, 4. I'll expand it 3 times vertically, move it right 1, and move it up 1. 3, 13. And I guess I should find out what my y-intercept is. So let's see what happened to this point right here. This is from your chart above, that's -1 and 1/2. So I'll take my y coordinate, multiply it by 3, then move it right 1, and then move it up 1. Oh, so now I need to find out what's 3 over 2 up 1. I need a common denominator. So that's 5 over 2, 2.5. So my new y-intercept is now 2.5. Any idea where my asymptote will move?
Up 1.
Up 1. The only thing that can move an asymptote is a vertical translation. Okay, so this is the only thing that can move the asymptote in an exponential function. There will be vertical asymptotes. We're going to see that at the end of the notes today. But for exponential function, the asymptote is always horizontal. And you can find the asymptote just by looking for the vertical translation. This graph really doesn't look like it got 3 times steeper. It looks like it has the same slope. But that's because we moved it over. Okay, so you can use that principle to draw any transformation of an exponential function. We can determine some of the aspects of this graph. So right below here, we'll write down the domain and range and everything. So the domain of an exponential, as you can see, it goes left and right in all directions. There's nothing that it's not allowed to be. So x can be any real number. But the range has some restrictions. What's the range of the function? Y has to be bigger than 0. Can it be equal to 0? No, because there's an asymptote there. We'll never actually reach the asymptote. Oh, I'm sorry. Yes, this is the original function. I was doing the black one. This asymptote is at 1, so y has to be bigger than 1. That's why I chose the color red. Yeah, we're doing the transformed graph. The asymptote is the x-axis, also known as the line, and again I did it for the other graph, y equals 1. And you can always find this as your d value, the last value, your horizontal or vertical translation value in your graph. It's always this last constant term. That gives you both the range and the asymptote. The intercept is a little bit harder to find. To find the y-intercept, you can take your graph and plug in 0 for x. And as you can see from our calculations, that becomes 5 over 2. and there's no x-intercept. It will never cross the x-axis. Okay, so for example, if I gave you an equation like y equals 5 1000 to the power of 20x minus 10 plus 3. Do you know where the asymptote is? 3. And the range? And of course I wrote 0 and I said 3. Greater than 3. So without doing any graphing, you can find out the asymptote and the range of an exponential function. It's always the vertical translation. Now in your homework today, you're going to have some questions kind of like this, where you're given an exponential function and a point, and you need to find out what are the values of the terms. So we're given that we have a equation y equals c 2 to the power of kx, and we're given 2 points. And what those points represent is they represent your x and y coordinates. So if you want to find out the equation for the function, you can plug in 4 for y and 0 for x. And then we could try to solve. 0 times k is still 0. And like we saw in the warm-up this morning, 2 to the power of 0 is 1. So c is 4. So now we already know that we have 4 times 2 to the power of kx. Now we just have to find out what k is. So now we'll plug in this point for x and y. So we'll plug in 256, and x is 12. So 256 is 4 times 2 to the 12k. We can divide both sides by 4. (256) is 2 to the power of 8. 4 is 2 to the power of 2. So 256 divided by 4 is going to be 2 to the power of 6, which is 64. So 64 equals 2 to the 12k. Now if I write 64 using the power of 2, then I can easily find out what the exponent is. 64, like I calculated up here, is 2 to the power of 6. I shouldn't have changed it. So if 2 to the power of 6 equals 2 to the power of 12k, that means the exponents also have to be the same. So 6 must equal 12k. And divide both sides by 12. And k is a half. So now that I know both of the constant terms, I can plug it back into the original equation. 1/2 x. And if you graph this function on your calculator, you could check the table of values, and you could see that, yeah, it does pass through the point 0.04, and it does pass through the point 12,256. I'm sorry that you don't have enough room there on your paper for that one. One thing that you really have to watch for with exponential functions is that you cannot combine these two. Okay. This is not the same as 8 to the power of 1/2 x.
Could you make it 2 to the 2 though?
You could. Yeah, if you wanted to simplify this, you could write 4 as 2 to the 2. And then you could use the exponent rules from yesterday, which says if you multiply powers with the same base, then you can add their exponents. So that's one way that you could change it. But you can't put the 2 and the 4 together and make it 8. That's probably the biggest mistake that comes out of exponentials, is thinking that those 2 can be put together. Now is where it gets interesting. The inverse of an exponential function. So we've already graphed 2 to the power of x many times. So let's graph it again here. Every exponential function has the point 0, 1 as a y-intercept. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of negative 1 is a half. And you can continue like that as you go closer and closer to the asymptote. Now what I'd like you to do is plot the inverse on the same grid. So this graph goes through the point 0, 1. So the inverse is going to go through the point 1, 0. And do the same with the other points. Remember, to graph the inverse, you can change the x and the y. I'll give you a minute to graph the inverse function. And see if you can identify the intercepts, domain, range, and asymptote. Okay, let's continue with doing this point by point. On the black graph, we have 1, 2. So on the red graph, we're going to have the point 2, 1. On the black graph, we have the point 2, 4. So on the red graph, we're going to have the point 4, 2. Three, 8 is going to become 8, 3. Negative 1 1/2 becomes a half negative 1, and so on and so forth. So this one gets really, really, really close to the y-axis. Okay. It's a reflection in the line y equals x. So here I'm going to write 2 pieces of information. First, we'll write the information about the inverse, and we'll compare that to the information about 2 to the x. So my red inverse graph has a vertical intercept nowhere. It'll never cross the y-axis. The horizontal intercept is 1, 0. see. The domain, well, it can't be any number. It's only positive numbers. Will that red graph ever be equal to 0? No, it can't get equal to the asymptote. But the range for the red graph, well, it goes all the way down. And if you keep going forever, it'll also go all the way up. Every number is possible. The asymptote is the line x equals 0. That's the y-axis. Now for 2 to the power of x, the vertical asymptote is 0, 1. But it doesn't have a horizontal asymptote. So if you take a look, remember, inverses switch x and y. So the vertical became the horizontal, and the horizontal became the vertical. You switch the x and the y. Same thing happens with domain and range. Domain is about x's, and range is about y's. So the domain of the exponential function is any number, and the range is bigger than 0. Everything about x became y, everything about y became x. And instead of having a horizontal asymptote, we got a vertical asymptote. X equals 0 becomes y equals 0. Now what's interesting is that this graph here is called log. The red one is log base 2 of x. Okay? Logs are just inverses of exponentials. That's all it is. So log base 2 of x is the inverse of 2 to the power of x. So now we'll do the same thing with 1/2 to the power of x, which we did on the first page. That's the one that's a reflection. And it gets really, oops, it doesn't cross. It gets really close to the x-axis as it gets bigger and bigger and bigger. But it'll never quite cross. There's an asymptote on the x-axis. Can you sketch a graph of the inverse of that function? Take about 3 minutes to do that. Okay, so usually the thing I like to transform first is the asymptote. In the beginning we have a horizontal asymptote, so the inverse is going to become a vertical asymptote. The point 0, 1 becomes the point 1, 0. Negative 1, 2 becomes 2, negative 1. And we can continue that pattern with the other points. Positive 1, a half becomes a half, positive 1. And as we get taller, we're going to get closer and closer and closer to the asymptote. And you could also figure this out with the flipping over paper trick. So you can find out those points just by changing the x and the y coordinates. So now to find out the equation, we just change the x and the y. That's what an inverse is. That's the equation. There's another way to write this equation. Yes, with a log. Any idea what the base of that log would be? 1/2. So we write a little 1/2 beside the log, and that means log base 1/2 of x equals y. That's the equation for the red line. Okay, so both these things mean the same thing. If you have a 1/2 as a power on one side of the equation, you can move it to the other side by making it the base of a log. And we'll learn more about that next class. So just to summarize, the first graph we saw is your most common log. Usually logs look like this. My favorite one is base 2. So if the base is a number that's bigger than 1, then the graph increases. When the base is a fraction, then the graph is going to decrease. And that's like what we did in the last example. When your base is a fraction, the graph decreases. Both of them have the same asymptote, which means that there's going to be no vertical intercept because it cannot cross that vertical asymptote. But the horizontal intercept is always the same. When x is 0, when y is 0, x is 1. And you could even check that by putting in 1 for x. Remember that this means that 2 to the power of what number equals 1? Yes?
Why is there a vertical asymptote?
There's a vertical asymptote, but there's no vertical intercept.
Oh, intercept, never mind.
Yeah, so vertical asymptote is going to be the line x equals 0. For both of them, the domain is only positive numbers, and the range can be anything. It's the opposite of an exponential function. So now we're going to look at some transformations of a log function. So let's say, for example, that we put in some numbers for A, B, H, and K. And basically, those numbers represent the things that we learned about in Chapter 1. So A is a vertical expansion, H is a horizontal translation, K is a vertical translation. How can we make the domain different? H. H would make the domain different. If H is a big number, then the domain that would move the asymptote over, then the domain would be bigger than H. So pretty much the domain is always X is bigger than H. That's the domain. Can B affect the domain? If you expand it horizontally, if you expand the graph horizontally, will the domain change? No. Because the asymptote would still stay in the same place. What about if B was negative? That's gonna flip it.
Yeah. So B does affect it?
B can affect it. Sometimes. If B is negative, then the domain is less than H instead of bigger than H, because you flip it over the y-axis. Now, the range is all real numbers. So if we do a vertical expansion on all real numbers, will it change the range? No. If we translate all real numbers up or down, will that affect the range? No. Nothing can change the range. The range will always be all real numbers.
What if not even A? Oh.
You can reflect it, you can expand it, you can translate it, but infinity will always be infinity.
Wow.
So if we expand the asymptote, will it move? How can we move the asymptote?
K.
K. Really? If you move the asymptote up, it's a vertical asymptote. You're moving infinity. H will move the asymptote. Because H will move the asymptote left or right. So actually the equation for the asymptote is always x equals H. So if you take a look at this graph here, you can figure out the domain and range without having to do any calculations. Do you know what the domain is? So the domain can only be changed by moving things left or right.
Like in the -2.
Right, but it's the 2 that's moving the graph. The 2 moves the graph 2 units to the left. So instead of having an asymptote at 0, now we have an asymptote at -2. So x will be bigger than -2. The asymptote will be at -2. So we can draw that right away. And the range will always be all real numbers, no matter what you do. Okay, so I'm going to draw the graph of log base 3 of x as a guide to start. In order to draw that, I'm going to think about it as being the inverse. Do you know what it's the inverse of? Very close. Not quite x cubed, but 3 to the power of x. Okay, so if you have a log on one side of an equation, it's the base of an exponent on the other side. 3 to the power of x is a graph that looks like this. It always crosses at 0, 1. And then the next most important point is 1, 3. Those are your 2 important points on an exponential. If you have those 2 points and the asymptote, you're pretty much set. So now, to graph the log, I'm just going to inverse that. So my basic log graph goes through 1, 0 and 3, 1. And then it gets really close to the asymptote when it gets small. And it goes through 9, 2, and so on and so forth. So now let me do my translations. The negative sign flips it, the 2 moves it left 2, and the 4 moves it up 4. This is the same thing as negative f x plus 2 plus 4. Okay, the function is the log base 3. So the log base 3 represents the function, because this one also has log base 3. So I have a reflection, translation, translation. So again, I can take this point by point. I'll take the point 1, 0. First thing I'll do is reflect it by changing all the y's. Then I'll move it 2 units left, and then I'll move it 4 units up. And that gets me my point on my new graph. I'll take the point 3, 1. I'll first reflect it by changing the y's from positive to negative, then move it 2 units left, and then move it 4 units up. So I get the point 1, 3. Now maybe I'll take the point 9, 2. I'll change the y's to negative, move it 2 units left, and 4 units up to get the 7.72. So if I connect the dots, it's going to gradually get smaller and then get closer to the asymptote as it goes up. So you can see how it reflected in the x-axis. Move 2 units left, move 4 units up.